Hello friends, welcome again. Few days back I have uploaded some videos on analysis of different subjects for GATE examination, and that analysis was for three branches: electrical, electronics and instrumentation. And I have also uploaded two videos on the circuit analysis, that was on transient response of first order RL and RC circuits. I got some requests from the students that I should take the core subject first. When I talk about core subject, analog electronics and EDC is core subject for electronics engineering, but not for electrical and instrumentation. So I thought of taking the topics and subjects which are basically important for all the three branches and common for all the branches, like circuit analysis. But students gave feedback that there are plenty of videos available on YouTube on circuit analysis. So rather than taking circuit analysis, I should go for EDC and analog, which is a core subject of electronics engineering. During the analysis, I have shown you the marks from different chapters of analog electronics, and we could find there are some chapters from which questions are appearing again and again. And there are some topics which are given in the syllabus, but we don't have questions from those topics. And this subject is important for instrumentation engineering as well, because there are plenty of questions which are coming from analog electronics nowadays in instrumentation engineering. As far as electrical is concerned, there are questions from analog electronics in electrical as well. And most of the questions are from diode circuits, BJT biasing, operational amplifier, these three topics, and few questions from small signal analysis. So, accepting your request, I will start with analog electronics and EDC. When I say EDC, the students from instrumentation engineering and electrical engineering may be thinking that this is not in their syllabus. This is not a fact. Basically, in electronics engineering, we have two different parts from basic electronics, that is EDC, and analog electronics, that is amplifier part. But this is combined in case of electrical and instrumentation, like diode circuits. So I will be considering EDC and analog as single subject. I have already told you in analysis, I uploaded on YouTube. And now we will start with the first topic of analog electronics and EDC, that is the semiconductors. Semiconductors is basically the very first and most important topic of this subject. Reason being, if you don't study semiconductors, you fail to understand all the devices, diodes, transistors, MOSFET, and if you fail to understand the devices, you cannot understand the operation of amplifiers. So therefore, semiconductors becomes very important topic from that point of view. It is important for all the three branches, especially from understanding point of view, but for electronics engineering, you have questions in GATE almost every year. And this is the topic which is important for engineering services as well. You have plenty of questions from this topic. There are basically two subjects which are having this topic as common, that is engineering materials and EDC. So nowadays analog electronics is important for all the three branches, but its weightage varies from branch to branch. For example, in case of electronics engineering, we have seen almost 20 marks weightage is from this single subject, that is EDC plus analog, and 5 to 6 marks in electrical engineering, and sometimes even 10 to 15 marks in instrumentation engineering. So the very first chapter of this subject is, I'll say, EDC plus analog is semiconductors. In semiconductors, when you talk about syllabus given in GATE and engineering services, the syllabus is basically not given in detail. Then if syllabus is not given in detail, then what should be the domain where I should confine myself? Domain means what are the topics I should be studying from this chapter to handle all the questions in the exam. My dear friends, when you define the syllabus, you have to go for analysis. This was the very basic purpose of uploading that analysis before starting the subject. And in the analysis, I have given you the chapter wise analysis. But I told you when I was discussing about chapter wise analysis, you need to have topic wise analysis as well. And I have full analysis of all the subjects topic wise as well. In semiconductors, we will be talking about approximately 15 subtopics from which questions are appearing. And this is the domain you have to define. Remember, as far as books are concerned, Millman Helkias is best book for semiconductors as far as exam is concerned. But there are some questions which are not fully covered in Millman Helkias. For that purpose, you have two more books. One is Streetman and Banerjee. Second is Nieman. So you can refer second book, that is Nieman, Donald A. Nieman for this. So these are the three books which are more than enough for semiconductors, not only semiconductors but for electronic devices. All the electronic devices will be fully covered from these three books. The first book is Millman Helkias. You should always study Millman Helkias and then you can refer other books for this. In semiconductors, I will be talking about the very first topic, that is, I will say, introduction. We will see what is there in introduction. Then second topic, I will be talking about charge carriers in semiconductors. This will be our second topic. Then third topic, I will be talking about intrinsic semiconductors. In intrinsic semiconductors, we will have again subtopics defined. I will see while we will be taking this topic. Then fourth topic, I will be talking about extrinsic semiconductors. Then next topic, I will be talking about law of mass action. Law of mass action. We will see what is the law of mass action. Next topic, I will be talking about direct and indirect band gap semiconductors. Then next topic, I will be talking about electrical properties of semiconductors. We will see what are those properties. Then next is 1.8, that will be generation and recombination of charge carriers in semiconductors. Then next topic we'll be talking about is diffusion. After diffusion, we will talk about the Einstein relationship. Then after Einstein, we will talk about, that is, components of current. components of current in semiconductor. Then after this we will talk about the continuity equation. Then after continuity equation we will talk about the potential in, that is potential across step graded junctions. Then we will talk about the Fermi level. Then last one we will talk about Hall's effect. So in semiconductors, these are the 15 topics we will be talking about. These. As far as GATE exam is concerned, the questions are from these topics. This is important for GATE. Then this is very important for GATE. You will have question repeatedly from this. Then Einstein relation is important for GATE. You have question from this. Then components of current in semiconductors is important for GATE. Then Fermi level is important for GATE. Hall's effect, you don't have many questions from this, but it is also mathematical topic. There can be question from this, but these are important topic from GATE point of view. Remember, in GATE 90% questions are based on numerical, so we will focus on numerical. But before we start with these topics, you need to understand the subject. You should always develop interest in the subject because it is a core subject. Number two, you will be able to remember the different topics and formulas if you develop your interest in the subject. The very first topic of semiconductors is, that is introduction. So let us talk about introduction. When we talk about the semiconductors, remember, it is basically based on the electrical properties of the materials. When we say semiconductors, so let us talk about the different materials and their properties. We know any material is always composed of the very small unit, which is an atom. An atom is always surrounded by the different shells in which electrons are revolving. Basically, rather than saying atom, the atom consists of nucleus, which is composed of protons and neutrons, and electrons in electronic shells. So I'll say we have nucleus, which is very small part of the atom. Then we have electronic shells around the nucleus, and there are electrons associated with every shell. Now remember, every atom has these shells, and every shell has some discrete energy level. This had some energy level, this had some energy level, this has some energy level, and when we go at infinity, its energy level is almost, we say, 0. But when you move towards the atom, it will be having certain energy levels. So when you have a single atom, so we have discrete energy levels. Electron at this level has certain value, amount of energy. When you move this electron from this side to this side or this side, when you move this side, electron will basically release the energy. When you move towards this, you are moving against the force of the nucleus, you need to supply the energy. So when we have discrete atoms, so they have electronic configuration, you have already studied in 12th. So that electronic configuration we will not talk about. But when you have solids, it was atom in isolation, maybe in gaseous state, so this was atom in isolation. When you have material in solid state, we don't have this type of arrangement. Say for example, say you have a layer of atoms. We have one atom here, 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 and so on. When you have a periodic arrangement of atoms like this is a periodic arrangement. When you have periodic arrangement of atoms, we call that as the lattice. That is called crystalline structure. So in other way we can say, in case of crystalline solids, we have periodic arrangement of atoms. Now, when we had energy levels as like this, similarly like this, we had a set of energy levels. Similarly here we have energy levels, and that is how all the atoms will be having their own energy levels like this. But see the important observation here, when we have electron here close to this, it has certain energy level, but when you move away, the energy levels are overlapping. Or rather than saying that, when you are moving the atoms in a regular fashion close to each other, the energy levels of the atoms start overlapping with each other. So see, suppose you have an, in that case, this electron belong to this nucleus at certain energy level, this electron belong to this nucleus at certain energy level. So it means we are not able to define the discrete energy level when you have the atoms arranged in crystalline structure of the solids. In that case, we don't define the discrete energy level, rather we will say there is band of energy levels. This is forming a band. So we will call, in case of crystalline solids, rather than defining the discrete energy level, we will define the band. If you draw the diagram, that is energy level diagram, this is called band theory of the crystalline solids. This is energy level, this is interatomic distance. Interatomic distance. Here you can please see, when the interatomic distance is large, there were discrete energy levels like this. But interatomic distance means what? The distance between the center or nuclei of the two atoms. So when you start reducing this distance, when you are bringing the atoms closer to each other to form the crystalline solid, in that case you are reducing this distance. You are bringing this distance backward, reducing. So in that case, you don't have the discrete energy level, rather these energy level start splitting like this. And in that case, it will be like this, something like this. Means when I reduce the distance below certain critical distance, we are not able to define the discrete energy level. Why? Because this level is not belonging to this atom alone, this is belonging to level, is belonging to this atom also, this also, this also. So we will say band, energy band, and it is becoming band now. And at certain point of time, at certain distance, when we have the distance defined for solid, say this. Say this is one typical case for a particular solid. Say this is the distance r, suppose that is there in the crystalline solid. In that case, that was split, this was split, so there is certain gap and electrons can occupy this state but no state in between. They can occupy this state but no state in between. And this state and this state, these are no more discrete levels, rather band. We call this portion as valence band, and we call this portion as conduction band. I will let you know what are valence band and conduction band. When we reduce the interatomic distance, then there are no discrete energy levels. Reason, because no level is belonging to one particular atom, this level is belonging to different atoms, so we call it band, and this is called valence band, this is called conduction band. Now let us see in this figure. I'll say when energy level is low, electron is basically, I'll explain with red marker. When electron is of particular atom, it is having force exerted on the electron more by this nucleus. So electrons in this area, this is the area closer to one particular nucleus of an atom, so we will call this area as valence band. In that case, electron will remain here only. But further, if you move away from this atom, we have suppose this portion, this is the portion, rather I'll say, you can see this is valence band of this atom, this is valence band for this atom, this is valence band for this atom, and so on. But there is some portion, maybe here, maybe here, maybe here. So there is certain portion. If electron is here, suppose, then there is certain amount of energy required to bring this electron out of influence of this nucleus. So this portion is belonging where force due to this, due to this, due to this, due to this is almost equal. And when there are multiple forces acting in different directions, the net force on the electron is 0. And if net force on the electron is 0, that is free to move. And if it is free to move, then that portion is called conduction band. So the area near the nucleus of this atom is nothing but valence band, where electron is belonging to this atom alone. It will not move out. But if you supply some amount of energy to this electron, it will come to this due to all the atoms are neutralized and electron is free to move. That portion is called conduction band. Conduction band and valence band are defined in terms of energy. Here it has certain energy, maybe this. Here it has certain energy, maybe upper one. So if you expand this portion of band, basically energy diagram or band theory, you can say energy band, I'll say like I'll be able to draw the expanded portion of that small portion, this and this. I'll call this as the valence band. I'll call this portion as conduction band. And this level I'll be calling as highest level energy level of valence band, and I will be calling this as conduction band. And this gap between valence band and conduction band is called band gap or energy gap. And this is purely the property of a material. For example, there are certain materials where when electron is here, it is having almost equal forces by all the atoms, it is free even belonging at this energy level. Such type of materials where electron is always free are called metals, conductors. And when electron here is bound to this nucleus, but it requires certain amount of energy to move in the region where forces of all the atoms are equal. So that energy required to move from here to here is band gap. And band gap is property of material. It is specific to a material. So now, rather than having discussion on this part, I will directly come to this part. So I will be discussing about the band theory of crystalline solids. What is the meaning of crystalline solids? The crystalline solids are the materials in solid form where the atoms are arranged in periodic fashion. When atoms are arranged in periodic fashion, then there is a unit, three-dimensional unit, which is called smallest three-dimensional unit, called cell. Cell is the smallest unit of any three-dimensional structure. So now here what I find is this plays very important role. When the band gap in any material is of order of 1 electron volt, when this band gap, it means when electron near the nucleus is bound to that nucleus itself, and if I supply some amount of energy equal to 1 electron volt, it moves in the region where it is free to move, then the material is called semiconductor. Remember, semiconductors are the class of crystalline solids where the band gap is of order of 1 electron volt, maybe in the range of 1 electron volt, not precisely equal to 1 electron volt. For example, germanium is one material which has band gap of, I hope you remember that, the band gap of germanium is 0.785 electron volt at 0 Kelvin, and it is 0.72 electron volt at 300 Kelvin. It is a semiconductor. This is for germanium. Similarly, for silicon, again a semiconductor, band gap is 1.21 electron volt at 0 Kelvin, and it is 1.12 electron volt at 300 Kelvin, which is considered to be room temperature, adopted universally. So now what we find, the materials in which the band gap is of order of 1 electron volt are called semiconductors. Now we are left with two more materials. Basically, when we talk about the band theory, we classify the material into three categories. One is semiconductors, I am talking about. Second is when this band gap is very high of order of 6 electron volt, then the material is called insulator. Why? Because I need to supply very high energy from here to here for moving the electron. Otherwise, at normal temperature, at room temperature, all the electrons are here. There is no free electron to move. There is no conduction. Conduction is always associated with free electrons in conduction band. If there is no free electron, there is no movement of electron, there is no current in the material. So now, there are some class of materials where this band gap is 0 electron volt. It means electron is always free to move. There is nothing like conduction and valence band, it is free to move. That class of materials is called metals. So my dear friends, remember, from band theory, crystalline structure point of view, we have three classes of materials. Semiconductors having band gap of order of 1 electron volt, insulators having band gap of order of 6 electron volt, metals having 0 band gap. So I hope you are understanding the band theory, and I will not be taking much time. I will be uploading videos on small topics so that you don't lose your interest and you learn more. Next topic I will be taking, that was basically the charge carriers, the concept of charge carriers in semiconductors, wait for my next video. Thank you very much.